Okay, thank you, Kenneth. This site presentation is a bit of a regular now for Compute Canada. I'm presenting this slide deck in cooperation with my colleague Maxime Boissonneau, and also Ryan Taylor has in the past contributed to these slides. So we're mentioning him as well, but he's probably still sleeping because he's in British Columbia, where it is around 6:15 a.m. at the moment. And we're speaking on behalf of the Compute Canada Research Support National Team. So that's a team that is mostly responsible for installing software, but there's some other tasks as well, namely the ticketing system and the user documentation. So our presentation outline is where we were, where we are in Compute Canada. Well, there's supposedly a lot of changes going in that we're going to be reorganized in the coming years, but that's a completely separate topic. Our software installation, our goal and design overview, the tools that we used, which is a combination of CVMFS, Gentoo, which used to be Nix, and EasyBuild, of course, Elmod and Python. And we do monitoring, a little bit about monitoring documentation. We don't have time for a demo this time. I accidentally left that in. So what is Compute Canada? So Compute Canada, you could see as a collaboration between different regions and sites within Canada that administers the academic supercomputers here. There are other supercomputers too, of course, that are outside the scope of Compute Canada. For instance, the Weather Forecasting Organization, Environment Canada, has big supercomputers themselves that also show up in the top 500, but we're looking at the academic side here. And Compute Canada in itself is composed of 4 regional organizations. Some have sub-organizations as well, but they're out west. We have WestGrid, we have Compute Ontario. For the province of Ontario, province of Quebec, we have COCO Quebec, and then in the eastern Atlantic provinces, there's AceNet. About 200 technical staff distributed among many universities, and more than 15,000 user accounts, professors, postdocs, students, you name it. Some people in government organizations as well, like research institutes. Across all kinds of disciplines. So we see here a diagram of where they come from. There's a lot of growth in non-traditional disciplines like HPC. Traditionally is a lot of physics, computational fluid dynamics, and things like that. But we've got a lot of growth now in bioinformatics, in health sciences, in digital humanities as well. So the ARC platform has these 4 organizations, and there are some national clusters and some regional clusters as well. So the national clusters are accessible by all researchers in Canada, and of which we have 4 HPC clusters. They are Cedar, Graham, Niagara, and Beluga, and a cloud system called Arbutus. This was also discussed in the previous talk by Félix Antoine. And so when we were getting these national systems in place, replacing a lot more what we call now legacy clusters, we wanted to have a system that was as consistent and easy to use as possible across all sites. So no matter where users log in, they get a very similar interface, whether they log into Graham, Cedar, or Beluga. Niagara is slightly different because it's not a general purpose system. It's purely CPU only MPI for larger jobs. So they have kind of a separate stack. They want to go their own way, but our stack is also available on that cluster. So we want to have all software accessible on every site. It should be reliable, performant, and we want it to be independent from the underlying OS stack. So whether it uses CentOS 7 or CentOS 8 or some other Ubuntu or some other Linux distribution, it should still work. We want to automate as much as possible, and we want to make it easy to use this large and evolving software stack. So we need a distribution mechanism. We chose early on to use CVMFS. This has been discussed extensively, so it doesn't need much more introduction than that. We have an independent compatibility layer, which uses Gentoo. It used to be Nix. This was also introduced in the Easy presentation by Bob Dreuge, and we had a presentation from Gentoo itself as well. And automate installation via EasyBuild. And then we use lmod as many others. So luckily, all of these things were already discussed during the EasyBuild user meeting, so I can go quickly over these slides. We have a process that's mostly user-based. So except for the basics, we usually a software is only installed. Software pack is only installed if a user asks for it. So we have a ticket. I want to, can you please install software XYZ for me? And then we create an internal software installation ticket where we install it on a build node where there's a bunch of installers, about 10, 15 people who regularly install software, where we share 2 build nodes that are cloud VMs. We install on the build node. We can install in our home directory. We test on the build node, and then when it's working okay, we can install centrally and then push it into CVMFS, for which we also have a development CVMFS and a production CVMFS instance. So we can publish it first on the development instance, then test it on the test node or on the clusters directly via a helper utility called proot. And then we can publish it to production, and then we inform the user, hey, it's available on the clusters. Please let us know if it works for you, and then we're done. Sometimes there's software that's too specific, or a user asks, can you install the latest snapshot that's just a master checkout of Git repository XYZ? And then we say, no way, we're not installing unstable software globally. You can install it yourselves. And then the user, either we install it in the user's account ourselves manually, or the user sometimes can use EasyBuild themselves, because we have that all set up to install in the user's home directory as well. And then it will just show up as a custom module. So this is the software stack is continuously growing. Maxime has been so kind to update this graph, and we're seeing we started this whole process in 2017, and right now we're, as you can see, it goes all the way into mid-January 2021, where we're now. And there's been some growth spurts when we added new architectures like AVX512. You can see in terms of numbers, bioinformatics is the king of a number of modules. This shouldn't come as a surprise because of the enormous diversity of packages that are used by bioinformaticians. So you can see how we now are nearly at 8,000 software packages, including all the variety architectures, etc. So our design overview, it must look familiar because you've seen a very similar overview in the Easy presentation by Bob Dreuge. That's not a coincidence because they used our overview as a template. So this year, what we've done is to move from the 2017 base stack with Nix to a Gentoo base stack with the number 2020, because that's when that particular Gentoo version was released. Well, you couldn't call it exactly a release. It's a snapshot. So it's just a rolling release where we took a random date from May 2020. So we have at the top the EasyBuild layer. So there's multiple architectures, and we put that in a particular path modules software with 2020, and the older modules are for 2017. Then we used to have some middle layer with EasyBuild-generated modules around Nix profiles that looked like a good idea at the time, but we got rid of them. It makes the system a bit simpler. And we moved all these things that were compiled with Nix and then have EasyBuild-generated modules around them. We moved them into pure EasyBuild. So all ththese packages, TC, Eclipse, Qt, Perl, Python are all EasyBuild packages now. We used to use Nix for compatibility layer, but just like Easy, we're now using Gentoo. We're getting into more details in the next slide of why we changed from Nix to Gentoo. And then under the compatibility layer, there's a gray area which we also put in Gentoo, but it can be overwritten using LD library path if you want to. That includes things like the Lustre client libraries and lower level client libraries for InfiniPath, OmniPath, and things like libIBverbs for the InfiniBand stack. Packages like UCX and libfabric that are a little bit higher level than IBverbs. They are compiled using EasyBuild, much like in upstream EasyBuild. And then at the bottom, we have things that are local. Those are things that are very intertwined with kernel modules or the kernel itself, and some things that we have legal restrictions on, like FASP, that are not allowed to be distributed, even in a restricted repository. So the next part is why did we what are the difference between the old Nix stack we had in Gentoo Prefix? So Gentoo, as was introduced in the Gentoo talk, it uses recipes much like EasyBuild, except they're written in some kind of bash-like syntax, and they're called ebuilds, but otherwise there's a lot of similarities between a Gentoo ebuild and an easyconfig file. We use them to provide dependencies for scientific applications. We provide glibc itself, but we also provide many things that EasyBuild provides in the compatibility layer that are kind of boring and they're not scientifically interesting. Things like libxml2 and many other things that are that EasyBuild does provide as modules because what the OS provides is often too old. We put in the compatibility layer we added to filter depths. We provide that abstraction layer as a module. So when you install Gentoo Prefix, you get a bash script that allows you to enter the prefix environment. We use a module instead to set a lot of the same environment variables. And then we have most of the dependencies of the scientific software stack. So our Gentoo Prefix layer is basically a checkout from the rolling Gentoo distribution, namely a file that I downloaded on May 4th, 2020. And then we freeze that. There are no version updates except for a couple of customizations that we put in a special overlay repository, a Gentoo overlay, where we have to make some changes. Sometimes there are bugs in Gentoo, sometimes they're just customizations that are more local. So swapping the module from the older Nix to a Gentoo feels like a Linux distribution upgrade. It just makes everything newer. It's like you do a EUM upgrade on a Fedora distribution and just boom, all the basic tools are certainly newer. So the big change is a GNU libc version change, where in the older Nix layer we had 2.24, we now have version 2.30. And that actually has some implications for HPC because a lot of changes went into the libm library in glibc. I put a link here in the slide deck. Later on, you can probably click on there when I make the slides public. I'll send the slides to Kenneth. So one thing is that a lot of effort went into optimized math functions like the exponential, log, pow, etc. The older glibc was extremely precise, up to 1/2 unit in the last place, which is the most correct you can get, but it paid by switching to multi-precision arithmetic when needed. It meant that for some inputs of the exponential function suddenly went like hundreds of times slower than for other inputs, which confused many people. And now they made it faster, but at a slight cost of precision for those edge cases. And actually, there are some examples. There is one example from Damien, who works at Jülich, where he said that there were big difference between the libm speed of GNU versus the one in libimf from Intel, and those differences more or less went away with the newer libm. So it benefits everybody by having just this newer libm than what we had before. And then many other things then change, like we have a newer bash, we have a newer git, we have a newer vim, Emacs, etc., etc. So why did you switch to Gentoo instead of Nix, and why kind of also a reason why Easy uses Gentoo is like in Nix you have a very self-consistent system, but when you put things on top of Nix, the whole system breaks down. So Nix is very beautiful, much like GUIX, but you have to stay within that environment to make it work properly. And the reason is that in Nix, what you get is a symlink forest where you have a profile, you get things out of that profile, but the profile itself is a symlink. The version points to a generation, like in this case 523, which in turn links to a hashed path, and in the hash path you have the actual binaries, which in turn point to the hashed location of the package, in this case core utils for ls. Now we wrapped the LD, the linker, so that all paths point to this to Nix user profile /lib, so the first location here. But what happens is that when you upgrade a package because some bug fix or something like that, the package gets installed into a completely new Nix store location with a different hash. And what sometimes happens that these hashes, they leak through the environment, even though we only advertise these, the top level link. What happens sometimes that software packages, they resolve symlinks, and we have these store locations leaking into user make files or something like that. And what happens is that when we upgrade a package, we can garbage collect the old location, then the old location no longer there, and things break down on the user level. And that's fairly hard to control. And we found out that Gentoo Prefix, it doesn't have these symlinks, it just stores directly in the location, and we kind of eliminate that. So Gentoo Prefix is like the minimal solution for what we need, whereas Nix has a lot of extra things, which is in principle useful, but it sometimes hurts us. Now, on top of the Gentoo layer, we have what we call standard software environments. I put a link here where it's explained in our wiki. And so some combination of modules is loaded by default on clusters, so that when people can use GCC and Intel compiler as soon as they log into the cluster, and they don't have to load any modules themselves before using a compiler. There is some disagreement about that. Some people like it that no modules are loaded by default, and people should get a minimal environment and they have to load whatever they need. But we had some majority that said, okay, we should load something by default, which makes it a little bit more user-friendly. And we call those standard environments. It's possible to go outside that structure. We also have like Intel 2017 installed and Intel 2019, but that's the default, which usually uses C, and it's what we compile the most packages for. The other ones we install only a small subset of packages for people who have a need of different compiler versions. So the workhorse for a few years has been 2016 compiler and GC 5.4 on the cluster Cedar and Graham that were brought into production in 2017. On the newer Beluga cluster and partly on Niagara as well, we use GC 7.3 and Intel 2018 with OpenMPI 3, and that's still using the same Nix stack as as the 2016.4 standard environment. And now we're working on the newer Gentoo based environment, and we're making the default in April this year. And that actually corresponds to upstream EasyBuild IOMKL 2020A. So it's kind of a mix between FOSS and Intel. It's mostly the Intel toolchain, except that we use the OpenMPI instead of Intel MPI, because we find that the runtime architecture works a lot better for us with OpenMPI than with Intel MPI. And so we have Gentoo TC 9.3, Intel 2020.1, and OpenMPI 4.0.3. We have multiple flavors for architectures, except for the system toolchain, for which we have architecture independent, so it uses generic SSE3. One thing we've changed versus the 2017 stacks, like the 2018 and 2016 standard environments, is that we now have fat binaries using the Intel compilers. That helps on clusters that are heterogeneous. We now have particularly the Cedar cluster. It has login nodes which are Haswell or Broadwell, and it has a lot of newer worker nodes that are Skylake. And so we want to make sure that the binaries are optimal, and sometimes users submit jobs and they don't know if those jobs end up on Skylake or Haswell processors. So we want them to have optimal performance no matter where they end up. Some other things that we do a little bit different from upstream is that we have a lot of modules at the core level. We compile them with GC Core 930, but they end up in the core part of the module hierarchy. And we even have that for things like R, Julia, many bioinformatics tools, basically anything that doesn't use either MPI, Boost, Fortran, ACF5, FFTW is heavily factorized that can benefit from Intel compiler. We compile with TC Core and it ends up at the core module hierarchy. So that's kind of different from upstream, because upstream has a separate hierarchy for TC Core with a version, and we can make that work by everything by a central lib standard C++ library and libc Fortran library. So by doing that, we basically take advantage of the fact that lib standard C++ has version symbols, so it is backwards compatible, and this makes it possible to collapse different GC Core versions into a single location. It's a little bit tricky, but it helps users who compile their own software. It always use the same lib standard C++, so we don't have things that accidentally try to load different standard C++ versions from different locations because they were compiled at different times. Another thing we do differently from upstream is that we install Intel MKL at the core level, which means we get all the functionality except for the MPI wrappers of FFTW. And we even have a tool chain that I stole from Yuli, which is called CC Core MKL, which combines CC Core, but it can use MKL because MKL is installed at the core level. We can combine the two for the packages R and in particular. We use RPath, but we don't use EasyBuild's RPath support. We use our own linker wrapper, so it actually is also used if users compile their own software. If the wrapper if it links to things that are installed via EasyBuild, and if so, it injects the RPath in the binaries. We use RPath now instead of runpath, so we can no longer overwrite this with LD library path. However, the advantage is now we have RPath inherited by runtime plugins. That's a bit complicated, but runpath sometimes is not inherited, and that means that we lose the information in shared objects, and that gives us very annoying bugs at times. So RPath has that other nicety. So with StdEnv 2020, we have a bit of catch up to do. We had 800 different software packages installed in the older stacks. So we had to recompile pretty much everything, except that we thought, okay, let's put in some priority. We made a list using module logs. We identified which packages were used the most often, and then we made like a top 800 list, and we started from top to bottom and say which ones needed priority in recompilation, because there's often users who ask for a software package to be installed, and then they use it for a bit of time, and then the user graduates or disappears, so there's no reason to install it, reinstall everything. We just need the ones that users use. We have some unresolved issues that are mostly about just upgrading software. That's what happens over time. We found some bugs, like saying, oh, we use a tag number in OpenMPI, MPI sent and MPI received that was like a tag number of 1 billion, and suddenly didn't work anymore. And actually, that was not permitted by the MPI standard. It was out of spec, but it just happened to work with older MPI, which uses OpenIB. And now with UCX, it doesn't work. But anyway, this is kind of the things that we keep running into when software is upgraded. People find that the software, for some obscure reason, doesn't work anymore. It's just what happens as software gets upgraded. We still have some things we need to work on too. Parallel I/O doesn't work optimally for some people. That's always a complex issue. There's some library that can speed up communications on collectives using the hcall library. We installed it in the compatibility layers, the Mellanox library, but we found some issues with it, so we work on that. And we also have virtual GL in the compatibility layer for using GPUs on worker nodes. That's some of the minor things we still work on. Another thing we've used a lot more in the newer stack is to have Python extensions with multi-deps. So if a Python support exists, we install with Python 3.6, 3.7, and 3.8. So it's not just like upstream EasyBuild is one Python 3 version plus Python 2.7. We have multiple. We install it for multiple subversions of Python 3. So in this case, 6, 7, and 8. We don't have 3.9 installed yet, because we haven't had anybody asking for it yet. I'm sure it will happen in the future. So examples are things like BoostGIS, GGIS, and OpenCV, many other packages. So what people do is that they load a module, Qt5, for instance, and they get PyQt installed as a Python binding. So we just make that easier for the user, and to say, okay, we want to load a Python module and have some Python functionality of the other module, and then we don't say, okay, you have to load another module on top. We just have it in a single module. Some people disagree with that approach. We found it helps the users. However, for many other Python things that are pure Python and don't need another module, we have an extensive Python wheel infrastructure where we have our own wheelhouse. And so the standard of Python distribution are wheels. And because our environment is a little bit different from what the Python world calls, what's the word again? The binary packages that we can install from PyPy, they often don't work on our clusters, so we provide our own wheelhouse, so users install those instead. So we tell users when they want to install most Python packages like TensorFlow, set up your own virtual environment and use pip install Python package, like pip install TensorFlow. It gets installed in their own virtual environment, and then they can use that. So that gives a lot of flexibility in terms of which Python packages people want to use. We have some Python packages via modules like these extensions, We also have a SciPy stack module for the most common scientific packages, NumPy, SciPy, and Matplotlib, things like that. This is an example of the wheels. So we have at the moment more than 8,000 wheels installed. It's quite a lot of Python packages. And we can use the command avail wheels to see which ones are installed. So these are TensorFlow, for instance. You can see that we have 2.3.0 installed for Python 3.8, 3.7, and 3.6. So what modules are users using? We send that to syslogs, and we have a nice graphical interface. We can see what people are using Grafana. So here, this shows which modules are used. It's a snapshot of a couple of years ago. We can see we can exclude users. We can exclude some modules, and we can see which then, given the description, what modules are used. So this was kind of the things that we used to also identify which modules were used more often in the older stacks to see what needs to be compiled for the newer standard environment. So this brings me to documentation and resources. So we have our list of modules on the user-facing wiki, but we also made, last year, we made the technical documentation public. So there's now a GitHub based technical documentation about the compute Canada software stack. I know that the people on Easy refer to it quite a bit. So that's also one of the reasons why we made this public. And basically anything that's not confidential and we have to keep in our internal Google Docs based documentation has been put in that software stack. So if you want to know more about our software stack internally, it should be all there. If not, please let us know. You can use the public side of our software stack as well using this wiki page accessing CVMFS. So that allows you to mount it much like Bob showed in his talk for Easy. You can access our CVMFS as well, even on Windows with WSL2, and we can use all the software you like. So that's the end of my talk. Hope I didn't go much over time. A little bit.
Thank you, Bart. Does anybody have any questions for Bart? Jorg has a question, so I will pass across to him.
Thanks for a very interesting talk. One quick question. You've mentioned that you had problems with Nix and the Python virtual environment. Do you happen to know if Anaconda has a similar problem if you're using Nix?
Anaconda and Nix. I'm sure we've seen many issues with Anaconda. So if you would combine a Python from Nix with Anaconda, I'm sure you'll find all kind of weird issues going on there.
Thank you.
Because basically when you install the underlying issue is when you put something on top of Nix, you are getting outside the Nix infrastructure. So Nix doesn't know what happens on top of it. So whether you use EasyBuild, Anaconda, Spec, whatever, in combination with Nix, it's likely to break down somewhere.
Yeah, that was my suspicion as well from the problem you described with the Python environment. Thanks, very helpful.
Maxime has also raised his hand.
I wanted to add to this that the breakage we had with Python is virtual-env copies the Python binary, which was from Nix and included our path to the Nix store. And so when we updated something and garbage collected the Nix store, those RPath would stay in the user's environment because the binary was copied in there. I'm not sure how this would happen with Anaconda, but mixing an Anaconda with anything will give you headaches.
Yeah, we've when you go on our Python page, the wiki page about Python on Compute Canada, we basically tell users, please don't use Anaconda. It's entirely at your own risk, because we've had so many issues with people installing Anaconda.
I have to say thank you for that page, because we send our users to your page about not using Anaconda.
Yeah.
So I'm just seeing that somebody is typing, and I'm just wondering whether we're about to get a question in the Slack. Question is, for the Python packages in the wheelhouse, do you have multiple copies built with different architecture optimizations?
Yes, we do. We have various subdirectories, and so the great majority of wheels in the wheelhouse are architecture independent and are just pure Python, and so they are in generic. And there's a small subset that is in AVX2 or AVX512 subfolders, and it automatically detects where it should copy from.